Okay, so the energy equation, again, let's make our substitutions. So just writing this out, we have rho C U tilde U infinity times our partial. Now, okay, so we have to substitute in our theta. Remember, theta was, let's look back what that was. All right, so theta was T minus TS over T infinity minus TS. So if we solve that for T, we end up with theta times TS or T infinity minus TS plus TS. So if we now take that and substitute that equation in here, we're taking the partial derivative of that equation. So actually that last term or that last constant, the last TS that's there, that goes away, right? Because we're taking the partial derivative of that. So we'll just write it sort of after the fact of having that part go away, just because it's easier. So we end up with d theta, so we'll call it theta tilde, T infinity minus TS divided by d x tilde times L. Okay, so that's that first substitution. Then we have V tilde U infinity, our second substitution, d of, let's see, theta, T infinity minus TS divided by d y tilde L. Okay, so that's the left-hand side, and then the right-hand side is going to be, so we have a k out in front, and we have d squared of theta TS minus T infinity divided by d y tilde L squared. And then the last term is mu times d u tilde U infinity over d y tilde L, so that whole derivative squared. Okay, so that's our substitution. What we're going to do now is, again, we want to figure out how to normalize this. So we want to have like the terms on the left-hand side just without anything multiplying them. So let's take out everything that is common between those terms and divide out the equation, or divide out by the rest. So in this, let's see, we have T infinity minus TS. That's a constant, right? That's not changing. In this problem, we have U infinity that can come out, and rho C are also constant. So we're going to divide the whole equation by rho C U infinity T infinity minus TS. Okay, so we do that, and we are left with the following: U tilde d theta tilde dx tilde plus V tilde d theta tilde dy tilde is equal to, let's see, on the right hand we have k. Just going to write everything out here. So k T infinity minus TS over L squared times the thing we're dividing by, so that's L over rho C U infinity T infinity minus TS. I neglected to also include that L can come out here, right? So L can come out in that top equation. Okay, so that second thing is what we're dividing by, this here. Rho C U infinity T infinity minus TS over L. Okay, so we are that far. Let's see what else here. That is multiplying what? That's multiplying d squared theta dy tilde squared. And then the second term here is mu U infinity squared over L squared times the thing we're dividing, which is L rho C U infinity T infinity minus TS. And that's all multiplying, which I've run out of room, but I'll try to fit it in, is du tilde squared dy, sorry, du dy squared, that whole thing, right? Du tilde dy tilde squared. Okay, so we've got this far. So now we see, again, normalize. There's no dimensions on these terms, except we have a couple of groups that are interesting. So we have all this stuff here, multiplying d squared theta dy. And then we have another dimensionless group here, multiplying our viscous term, right? So we can go through and what can we do? We can, right, this goes away, the T infinity minus TS, that cancels. L is going to cancel. So we're left with, on the left, this one simplifies out to the following. It ends up being, so alpha over L times, let's see, U infinity in the denominator, times, let's multiply this by, again, nu over nu. And this ends up being 1 over Reynolds times Prandtl again. Okay, there's actually a name for this. So this is called the Peclet number, P-E, it's an E, or Peclet, depending if you're French or not. How do you spell that? P-E-C-L-E-T, Peclet. So the Peclet number is the product of the Reynolds and the Prandtl. That's just what it's called. And what it's giving us is a relationship between how important is the energy that's carried by the fluid. Right, this is some of the Reynolds number times the Prandtl number. How important is the energy carried by the fluid compared to conduction? Right, that's kind of what this is saying. Okay, then if we go on the other term here, again, sort of tight on space, but we'll do it this way. So we get rid of, let's see, we get rid of one of the L's. We get rid of U infinity, one of them. And we're left with, make some room here. So we're left with U infinity squared over C times T infinity minus TS, the denominator, times mu over rho U infinity L. Okay, so this ends up being, well, we see that there's a 1 over Reynolds number there. The rest of this stuff here, this thing here, this is actually called the Eckert number, right? Eckert number, EC. And what the Eckert number tells us, we know it has something to do with the viscosity term, right? Because it's appearing in the viscosity term. What it's telling us is how important is the thermal diffusion part of this problem, where you have this fluid shearing over itself, generating heat. How important is that compared to the energy difference across the boundary layer? Okay, so the Eckert number is kind of a non-dimensional measure of that. Combine that with the Reynolds number, and that gives you the importance, the overall importance of viscous shear, which is this last term. So a lot of times it turns out viscous shear can be ignored. That ends up not being an important thing, right? Reynolds number is usually big. Eckert number is usually not that big. But for certain flows, like low Reynolds number flows, really high viscosity flows, that term can become important, okay? So great, okay, we've gone through now and identified some of the most important non-dimensional numbers. Any questions on that? Nope. Okay, so what we're gonna do next time is we're gonna go through taking now our normalized equations and start developing correlations based on that. You probably could get started on, so the homework problem itself is going to be revisiting basically a numerical fin solution and then applying a convection correlation to that. So you could definitely get started with the numerical fin part of it, and then we can talk about correlations on Monday. Okay, have a good weekend.